Hello everyone, this is Mr. Kozlowski and welcome to Unit 4 Learning Target 3. Learning Target 3 states that you can diagram energy conversions using energy bar graphs, or what we call LOL diagrams. Essentially, we are still talking about the law of conservation of energy, which basically states energy cannot be created nor destroyed. It simply transfers from one form to the next. So what we have to do now is track that graphically, and we're going to use bar graphs or LOL diagrams. And LOL diagrams come from, if you look at the shape here of LOL, that's kind of the nickname that we have for them in class. So you're going to see these in chemistry, you're going to see these in physics. So anytime you hear LOL, it doesn't mean laugh out loud. It's basically referring to an energy bar graph conversion. So in this scenario, we have a bowling ball with no friction. It's basically suspended from a rope or a pendulum. And this is similar to the wrecking ball demo that we gave to you previously in Learning Target number 2. Now, we know that the total energy at the beginning of the motion event is going to equal the total energy at the end because we have, if we look at this system, we have no friction. So when we have that, we know that there's going to be a complete energy transfer. But let's start here at the very first one. The ball is held up. This graph represents the total amount of the ball's energy. We have 1, 2, 3, 4 bars, or 4 units of energy in this bar graph. So we know if there is no friction, we know that the law of conservation of energy states that we're going to have total energy is going to equal the same as the beginning as it was at the end. So we know what this is essentially going to be. So we can graph that, and I'll just do a little bar graph here. And to complete this bar graph, you go 1, 2, 3, 4. Now I like to label my bar graph like that because then it makes the math easier. It also communicates to me, if you do this in a problem, how many units of energy there are. And when we get to more complicated problems, that's going to come in handy because then there's a clear distinction about how much energy is converted from one form to the next. So those are the L's of the LOL diagram. Now what about the O? What does this represent? Well, this represents the total system, or the amount of energy in the system. And we know we're essentially talking about the ball only in this case. Well, since we know that the total energy is 4 when it's being held up than when it's at the bottom of the swing, we know that we're going to have the same amount. Why? Well, no friction. So no energy is essentially transferred from one into and out of the system. It is transferred from, this would be gravitational energy, so this would be EG, gravitational potential, and this would be, obviously, if it's moving at the bottom, this would be all kinetic energy, EK. So what we mean by no energy transfer is no energy is coming into the system or out of the system. So is energy entering or leaving? The answer is no. Energy is transferred from one form to the next form completely. We have 4 units at the beginning, 4 units at the end. We don't have to do anything with the O part here. So why do we have the O part? Well, that comes into play when we have friction. So here we have the same scenario. We have basically 4 units of energy here. And if we look at the total at the bottom of the swing, now we have 1, 2, 3 units of energy. So now essentially what happened was we lost some energy. Now you're thinking, how can that occur when the law of conservation of energy states that energy cannot be created nor destroyed? It simply changes from one form to the next. Well, the key part is it simply changes form from one form to the next. We know that this is all EG, all gravitational potential. We know at the bottom of the swing that this is going to be EK. However, can there be some energy conversion on the ball? And the answer is yes. We know that there's going to be some thermal energy here because we have this frictional force acting on the ball. So we know that energy is going to get converted to that form. So essentially, we say that goes into the air, and what we're going to do with this O part is we're going to draw a block of energy. So let's say this represents 1 here. And we're going to draw an arrow on top of that block, representing that the energy is moving or leaving out of the ball. So essentially, if we have this system here, we started with basically what we had. We had 4 bars of energy, and then the ball was left to swing. And if you think about it, we were left with a total energy of 3 units at the end. So this would be EK right there. This would be energy thermal. And again, why is that? Well, we have 1 unit of energy leaving the system. If we were to have energy entering the system, obviously we would draw the arrow inward towards the ball, okay, because energy is essentially leaving the ball. This energy in the whole system of the ball, we defined it as the ball. If we had the ball in the air, obviously total energy would be the same because thermal energy releases into the air itself. So that's the basics of LOL diagrams. You essentially have the energy before, the total energy after, and then you have how much is entering or leaving the system, depending on if there's friction or not. So what we're going to do is we're going to get a lot more practice on this. There's no quiz for this, so make sure you take good notes. I will be checking for this. And we'll see you guys in class. Thanks a lot.